Hello, and welcome to Lesson 3.3, Linearity and Continuity of Graphs. Our objective for today is that I can determine whether functions are linear or nonlinear, and I can determine whether functions are continuous, discrete, or neither. Now, a linear function is a function that has a graph that is a line. If the domain of the function is all real numbers, then the function will be continuous. A linear equation can be used to describe a linear function. It could look something like y equals mx plus b, or ax plus by equals c, or y minus y1 is equal to m times x minus x1. These are all three different types of equations that we are going to use to represent various scenarios. The top equation here, this one is in point slope form, and we've already introduced standard form, and you should know slope intercept form from 7th grade. Now we have some images here. In a discrete function, the points are not connected, and so we can see that they are just distinct dots all over the map. In a continuous, points are connected and form a line or a curve. So they don't have to be straight, but all of these points are connected and they are forming a curve, which means that all numbers are represented, whereas in a discrete one, only specific values are represented. And our third one, which is neither discrete nor continuous. Sometimes you have different things going on and it's not consistent. So some points are connected by a line or curve, but it's not continuous everywhere. And we see there's this big break in between these two line segments. So as we look at our domain and range information, the domain is the set of individual values when it is a discrete function, and so is the range. So we're just dealing with ordered pairs here. When it is a continuous function, your domain is going to be all real numbers, and your range is one interval of real numbers. So for example, in this one, the range would be greater than 5, because all of our values are going to be greater than -5, because all of our values are going to be higher than -5 on our graph. All right, so greater than -5, right? Because that's our lowest point. Everything else will be above it. All right. And when it comes to domain and range for something that's neither continuous nor discrete, it's going to vary, and you're just going to have to make it up as you go from one scenario to the next. All right. So we're going to look at our examples, and we're going to determine whether it's continuous or not. So our first one here, I have a curve that goes up. So it's trending down, then it goes up, and then it comes back down again. But all of those points are connected, so that is continuous. Our middle graph here, we've got a line segment there, we've got a line segment there, we've got a point right there. This is going to be neither. It is not made up of solely a curve that is connected. It is not solely made up of individual points, so it is neither of the two scenarios. Our last one here, we've got our points that are making a V shape, an inverted V. These are going to be discrete, because each individual point has its own point. There is no line that's connecting it. There's nothing else happening here. It's just individual points. All right. On our next page, we have 3 you-try problems for you. I want you to do those and then come back and check your work against mine. So the Bargain Book Barn sells young adult novels on a sliding scale. That is, the more books you buy, the cheaper they are. Let f of x model the store's prices for given quantities. Is f of x discrete, continuous, or neither, and explain your reasoning. So if I look at this, I just see a whole bunch of points as I go up my graph. So it is going to be discrete. And why? Well, It's distinct points, and the reason they're distinct points is because you can't buy half a book. Okay, you can't buy half a book, so you are only buying books in quantities of one, in counts of one. One, two, three, four, five, six, seven, etc. So you can't have half a book. Sorry. So it's going to be discrete. It's not going to be a continuous line where you could have fractional values of books. That doesn't make sense given the context of this scenario. Now, if we look at letter E, we have this fluctuating graph, up and down, up and down, up and down, up and down as time goes on. And while it changes, it goes up and down, it's got this repeating pattern, this is going to be a continuous graph because you are continuously fluctuating from one point to another, and there are variations, right? You could be right here where it's 45, 48% open, or it's all the way at the top here where it's 80, or down here where it's less than 20. So this is a continuous graph because it is a continuous fluctuation as the flower opens up. It's increasing in its openage, and as the bud closes back up, it's closing in its amount of it being open. So it's not like it's just jumping where it's closed in one moment and it's open in the next. It's a continuous gradual process, and that's why it's continuous. Letter F, we have days billed and we have total fee. And this is in the context of a lawyer, I believe, or an investigator of some type. So what the scenario is, we can see what happens here. From 0 up to 250 or so, that's kind of a continuous line. It could be in fractions thereof, but then once you get to a day, you have 1 day, 2 day. Now you're only billing in full day increments. So this is going to be neither. Now, some professionals will bill you per hour. In this case, it's something that's being billed on an amount per day instead. Now, we're going to go down the page and we're going to look at examples 4 and 5, which are linear and nonlinear functions. A linear function is in the form from yx plus b, or y equals mx plus b, when it is solved for y, where m and b are numbers. There is one exception, and I want to see if you can guess what it's going to be. So letter A, is this in the form y equals mx plus b? The answer is yes, so this is linear. 6 is m, -7 is b, 6 is my slope, -7 is my y-intercept. Now, letter B, we're asking, is this in the form y equals mx plus b? Well, the b is a number, the m is a number, but it's x squared, not x. So this is non-linear. And what this curve is going to look like is it's going to be a narrow U shape, and it's going to be at 2, moving up 2 on our graph. So if we had our grid, here's our grid, this would be 2, 1, 0, our origin. So you could see this is a U-shaped graph. It is nonlinear. It's not a straight line. Y equals -1. Well, let's see. Is this in the form y equals mx plus b? Well, we're told that m and b have to be numbers, and I clearly see a b value here, right? My b value is -2, right? That's that piece at the end there. Well, where is this? What could this possibly be? What value of m would make something disappear like that? Well, if our slope is 0, if m is 0, that'll make that go away, and we're left with just y equals b. So this is a horizontal line at -2. So this is linear. Now, I have 3 U-try problems for you to go through, and I want you to check your work against mine, and then we'll go from there. So letter D. This is not in the form y equals mx plus b, right? We want y equals m x plus b. Y is not by itself on the left, so let's get it by itself and see what this scenario is. So we subtract 8 from both sides, and we have negative 2y equals x minus 8. Then we're going to divide by negative 2. And we get y is equal to negative 1/2 x plus 4. Now that certainly looks like it's in slope-intercept form, so that is linear. Here's one of those that I referenced earlier. This is called point-slope form because we could extract a point out of here. But we're going to start by distributing 5 times x and 5 times 4. So we got y minus 10 is equal to 5x minus 20. Now, my next step is going to be to add 10 to both sides. And we're going to get y is equal to 5x minus 10. This is in the form y equals mx plus b, so it is linear. And our last one looks pretty similar to the previous one, but let's see if it is. When we distribute, we get y plus 2 is equal to 2x squared plus 10. And then our next step is to subtract 2 from both sides. And we get y is equal to 2x squared plus 8. Well, it looks really close to slope-intercept form. It's not. It is going to be non-linear. All right. So we're going to go to the next page now, and we have functions that are in table form. And we want to know, we're still looking at this concept of being linear. So a linear function is one that has a constant rate of change, ROC. And we are going to calculate the rate of change, and we're going to label each of these as either being linear or nonlinear. So our first one, we have deliveries and hours worked. So as our deliveries go up, we're adding 1 each time here. Adding 1, adding 1. And these we're adding 0. So if we're figuring this out, we are going to do our rate of change. So it's the hours per delivery, which is going to be the change of 0 over 1, which equals just 0. This is linear. It doesn't matter how many hours you work, your delivery rate is not going to change at all. So no matter how long no matter how many deliveries you have, you're still working 8 hours only. So this would be a horizontal line. Now, letter B, we have a different table orientation. This one's vertical. And again, we're going to do these little carets. We're going to look for the rate of change. How much is it going up on each interval? So from 7 to 13, we're adding 6. From 13 to 19, we're adding 6. From 19 to 25, we're adding 6. On the left side, from 0 to 2, we're adding 2. 2 to 4, we're adding 2. 4 to 6, adding 2. So our change in our rate of change is change in y over change in x. So that's going to be 6 over 2, which reduces to 3. This is linear. We have a constant rate of change. We're increasing by the same amount in all of our intervals, all of our steps. All right, I want you guys to try letters C and D on your own, and then we will go over them as a group. All right, letter C. We have the length and the width of a shape of some sort. And so from 2.5 to 3.75, we're adding 1.25. From 3.75 to 5, we're adding 1.25. Same thing here. And on our y values, our width, we're adding 0.5 to each one. So our rate is still going to remain constant. It's 0.5 over 1.25. So this is linear. All right, now our last one here, we have the width of the lot and the area of the lot. So the width, we're adding 20 each time. And our area, well, this time we're going up by 2,200. This one's going up by 2,600. This one's going up by 3,000. And this one is going up by 3,400. So is that the same rate of change? Are we changing the same amount every single time? No, we are not. So that is non-linear. Even though the x values are changing the same, the y values are not. This is actually going to be a quadratic. It's a squared graph. All right, now let's take a look at some graphing, and we're going to identify if something is linear or not. And these are going to be the most obvious possible ways that you can identify if something is linear or not. Our first example here, letter A, is a straight line. So that is linear. Okay. Example B, we have a curve here. This is clearly non-linear. There are 3 you-try problems. Take 30 seconds and try them on your own now, and then let's take a look at them. Letter A. This is that one exception that I talked about earlier. Did you come up with it? This is a linear function. Well, it's a linear equation. It is not a function because it fails the vertical line test. The equation here is going to be x is equal to 4. So that is the one exception to everything being able to be written as y equals mx plus b. This equation would be x equals 4. It is a linear equation. It is not a function because it fails the vertical line test. Letter B, we have this big curve going on here, and that is clearly non-linear. And letter C, now we have a horizontal line. This is y is equal to -2, and that is linear because it is a straight line. All right, that is the end of our notes for today. If you have any questions, please feel free to bring them to class tomorrow. Otherwise, have a great night.